So our next talk today is on model-based UVA test case generation. We've got the speaker today is Anas Shrina, Assistant Professor at the Applied Science University in Amman in Jordan, and Honorary Senior Research Associate at the University of Bristol with over 16 years of academic and industry experience. He has led the development of the award-winning UAV test case generator at SBFT 2025 and ICST 2025. Okay, over to you, please.
Thank you, Mike. Hello, everyone. My name is Anas Shrina. I'm an assistant professor at the Applied Science University in Amman, Jordan. And today I'll present to you our model-based UAV test case generator that I developed along with Dr. Chris and Professor Kristen Edda. This work was developed while I was working for the Trustworthy Systems Laboratory at the University of Bristol. In today's talk, in today's talk, we're going to let you know about the UAV testing competition, and it basically was part of the motivation for this work. And our winning tool, the pseudo-random UAV test case generator, that uses a low-fidelity path simulator. And then our extension, we've extended this method to use genetic algorithm-based approach to generate more diverse and better test cases. So this competition is jointly coordinated by the 18th International Workshop on Search-Based and Fuzz Testing, SBFT, and the 18th IEEE International Conference on Software Testing, Verification, and Validation. And this competition is the second edition that was carried. And the aim of this competition is to develop test case generators for UAVs that can produce effective and diverse test cases to basically identify underlying vulnerabilities in systems and system under test. Basically trying not to fly close to obstacles. So what's the test case? A test case in our scenario is a set of static obstacles, cuboids, boxes. And what we have to define is we need to specify each test case, specify basically the number of test cases, the position being the center of the base of this cuboid. It's 3D. You can see it here 2D, but we'll see another slide with 3D obstacles. And their orientation, they can be rotated around their axis and around the z-axis, and their sizes, length and width and height. At most, the competition allows for 3 obstacles. Obstacles must be placed on the ground. They must be taller than the flight height, so basically the UAV cannot fly over the obstacles. Obstacles obviously must not overlap, and they should be contained within a specified arena. And they need to keep the mission feasible. Keeping the mission feasible means you don't need to block the entire path. Okay, what do we mean by effective and diverse? So here a little bit of equations, but they are kind of intuitive. So the effectiveness of a test case, it's measured by how close a UAV flies to an obstacle. So this test case to the left-hand side, you can see the path taken by UAV during a test execution, and the minimum distance was 1.3 meters, could be in this point here, and this is the marking criteria. So if the drone, so basically if you generate test case, meaning that you have assigned boxes, static cuboids in the arena, that they force the UAV to fly very close within these ranges to an obstacle, you score some points. So if the distance, the minimum distance is less than 1/4 of a meter, you score 5 points, 2 points if you score between 1/4 of a meter to 1 meter, and 1 point if it's between 1 and 1.5, and anything more, any distance, in this case that causes the drone to fly more than 1.5 meter away from the obstacle, this takes a score of 0. So we mentioned that we need the test cases to be effective and also diverse. The diversity here is measured through similarity, and the similarity in this version of the competition, they have used this criteria. Basically, I have intentionally put two test cases, one on top of the another, and this shows how this similarity is being calculated by taking the intersection of the areas of the test cases, the dark gray here, with the area of the obstacles from the previous test case, the light gray, and dividing that by the intersection, by the union of the area, then taking 1 minus that value. So basically, if you have your test cases apart from each other, you get a better diversity score. This is, of course, is not the only way of doing this, and we are actually exploring how better we can measure diversity between these test cases. Chris will give more light on that. So each test case or test suite basically is being developed for a case study. In this case, a case study is a mission, it's a flying mission. You got starting point, waypoints, and the end points, the goal points. And what we do is we take this file that defines the mission, and then we place obstacles by defining their position, dimension, orientation, and then we run a simulation to see how good that test case was. The system under test is the PX4 autopilot, which is an open source UAV autopilot. Specifically, we are verifying the PX4 avoidance module, which is also open source. It's a vision-based, so the autopilot uses a camera, a dual camera, in order to navigate and avoid obstacles. And the PX4 avoidance module uses a local planner to plan the motion based on the 3D vector field histogram algorithm. This is the core of the avoidance system. Okay, so this is currently simulation-based testing. We generate test cases, then we simulate them. We use the earliest, which is a test bench that automates UAV testing. And this test bench uses high-fidelity simulation platforms such as like Gazebo to perform flight testing. The problem is high-fidelity simulators are computationally expensive, and to generate test cases, no matter what you try, what method you use, you have to evaluate many test cases. And this is actually the bottleneck in this problem. And this is what has been raised from the previous edition and this edition. How can we make test cases faster? So, and just to get an insight, simulating one test case with Gazebo, with these test bench, takes several minutes, up to 6-7 minutes. Our approach, by using low-fidelity simulator, we were able to roughly get up to 6 seconds time to evaluate a test case. Okay, so now we move on to our method uses two parts. One pseudo-random test case generator that uses a low-fidelity path simulator. The pseudo-random test case generator, we found out that if we use this, if we force the drone to take a path like an S shape, as you can see here, it's more likely we force the drone to fly close to the obstacles. And to do so, we decided we put one obstacle. We call this segment of interest, which is a link between any two consecutive waypoints. We choose that wisely to be in the middle of the arena. And then we place one obstacle with this angle, and we make sure that the segment of interest divide the obstacle into two parts, A and B. B is 2 times A, so 1/3, 2/3. And because, so this is also a good example of gray box verification, because these codes are open source, so we can peek into them, we can read them, we can see the algorithm, right? We can see the whole code actually, but we cannot instrument the code. So by studying the code, we figured out this algorithm, how does it work. We know that if we place the obstacle in this configuration, the drone will track along the A part and then will take a turn in order to go to the goal. And this will become clearer when I explain the cost function used in the method. And the second obstacle is just placed to maintain some gap to keep the mission feasible, a little bit longer to prevent the drone from circulating from beneath the obstacle. So it's a pseudo-random. That means we are choosing our configuration based from specified ranges, right? So I'm not going to go into these details. They are in the paper, and we will extend that into a journal paper where you can um, read more about our kind of intuition and logic. How did we do that? The main things is we start by randomly selecting the diagonal of the base of each of the first obstacle and the rotation angle, then the y coordinate. And there is kind of sequence that you need to follow in order to make sure that all test cases are valid and they don't overlap and they don't exist beyond the allowed arena. And then you need to choose the base of the length, which can be calculated directly from the diagonal and from the width, which is fixed to 2 meters, sorry, the height is 20 meters. Okay, the second place, we've already covered it. Now let's have a closer look. So how does it work? This is the test cases, these two static obstacles. This is on the left-hand side. I hope you can see my pointer. This is how the drone sees the scene, and this is the depth image extracted. Basically, this graphs here show how the drone sees the environment. It's when the drone starting from this side, the obstacles are far away from the drone. As the drone or the UAV get closer, this get bigger and bigger and bigger. Then the planner, the local planner, and as we're going to explain soon, it figures out there's this space here, and then it starts to take a turn right in order to get past through the two obstacles. And of course, this depends on the depth image, and this is how it works. Basically, it takes depth image, and from the depth image, this 2D image is converted into a 3D point cloud, where each point has the value of the distance between the drone and the obstacle. And from that, the algorithm 3D vector field histogram, it's convert this 2D picture into first 3D point cloud, then the 3D point cloud is converted to a 2D histogram. That allows basically each voxel in the space contains 1 point from the 3D point cloud. And where there is obstacles, that means this path is infeasible, along with some padding to maintain the safety. And the cost for the local planner, I'm going to explain just two of them quickly. So from each voxel, each cell in the space, how does the planner chooses which one to go to is based on cost that is combining multiple other costs. For example, here, we measure from each cell in the space, each voxel, we measure what is the difference in the angular distance between the drone when it will be in this point and the goal. So if the angle is bigger, that means this takes a high cost, right? It's less preferable. So we need to make sure that the node that we choose get us closer to the goal. In addition to the other cost functions, for example, maintaining that this is the direction, the headings of the drone, and the heading of this point when the drone becomes in here. So we take the difference between these two orientations, and we prefer nodes that make minimum change in the direction. Okay, so altogether, we start from a flying mission. Our software samples test cases from the predefined domains in order to make sure they are feasible and valid, and also critical in terms of they are chosen from our configuration to make sure that we have an S shape. This test case then gets submitted to our low-fidelity path simulator, which uses the same exact planner as the high-fidelity simulator. The only one difference is we are using the 3D open 3D algorithm in order to generate these depth images in order to guide the planner. So the test case goes to the local planner. The local planner from starting point send that along with the test case in terms of the obstacles location to a point cloud generator that basically give me the view that currently that the drone sees. And the local planner, we are using the same exact planner used in the high fidelity simulator to find out which is the next node. And then the next step, basically the second location, which we send to the point cloud generator, and we move on like that until we reach the goal. When we reach the goal, we assess the distance, the expected minimum distance between the path and the obstacles, or both obstacles. If it's less than 1.5 meters, we send this into the high-fidelity simulator, because this is kind of a candidate, is potentially good test case. And if the high-fidelity simulator confirm that the minimum distance is actually less than 1.5, we commit this to our test case. This is basically the algorithms to show that we start from a specific testing budget, and we start first by sampling a test case, evaluating it within our low-fidelity simulator. If it is good test case, we move on to the high-fidelity simulator. But if it's bad, we remain within this loop while we are not consuming any testing budget. We are doing local evaluation. Only when the test case is promising, we move on to evaluate it with the high-fidelity simulation, which decreases our testing budget. And then we do the same thing. We check if it's less than 1.5 meter, we accept it, or otherwise we check the testing budget and we carry on. This is the results from both competitions. We participated in the SBFT, but however, both this conference and this workshop jointly coordinated the competition, and eventually they announced the overall winner to be our method, named here as a pseudo-random. This is quickly the results. This is the failure score. They evaluated our methods on 3 test case studies, and as you can see, we did good on the case study number 2. Evolve 1 did better than us. Then on the second test case, we did even better, and we were the best basically. And the last case study, the last mission, was the most difficult one. As you can see, lots of test case generators struggle to produce any valid test cases for it. And in terms of diversity, you can see that most of the generators, that the tools that have participated, they have almost achieved similar score in terms of diversity. And also you can observe that the methods, the method didn't, the mission, the test case itself didn't affect the diversity. So the diversity, it was independent from the actual mission, because you get for the 3 cases same score for almost all methods. I also would like to note that the earliest is the baseline. This is a tool designed by the coordinators, by the committee itself, as a baseline. So the overall participants, they were 5 participants in this year. And this is the one overall score to show the kind of the ranking. The ranking also taken into consideration the length of the path generated, the time is taken to complete the test. And I hand over to Chris. Thank you very much. Hello, Chris.
Can you hear me okay?
Hi,
Ernest, can you hear me okay?
Yeah, I can hear you, yeah.
Okay, perfect. Okay, so building on the work that Anas just described, we were interested in finding an alternative way using machine learning to create diverse test cases. And for this, we introduced a genetic algorithm and a neural network-based critic at the start of this workflow. Now, conceptually, you can think of this as operating with many tests when they're cheap to evaluate, then refining to a smaller number as they become more expensive computationally to evaluate. Starting on the left, so the genetic algorithm initially starts with a random population of test cases that it operates on. And over time, these then produce a set of tests that are effective because we believe they cause the drone to fly close to an obstacle. And they're diverse because each test case is a different arrangement of the obstacles. And the crucial word here is we believe, because we've used a neural network-based critic to assess how close we think the drone will get to an obstacle. Because we don't completely trust the neural network critic, we then pass these effective and diverse test cases through the Low-Fi path estimator to reevaluate them and then produce a smaller number of test candidates that are then passed to the High-Fi simulator. And I'm going to go through the neural network-based critic and GA part because that's kind of the new part. So if you have the next slide, please, Anas, and the one after that as well. Perfect. Okay, so the neural network critic is trained on a data set. We used the pseudo-random test case generator to generate different configurations of the obstacles, and then we use the Low-Fi path estimator to apply the minimum distance label to each one of those obstacle configurations. We then train the neural network critic on that data set. So effectively, the neural network critic becomes an approximation of the Low-Fi path estimator. Next slide, please. Okay, from the GA perspective, so this approach I first saw when we were conducting the review. It was used for generating test cases to find bugs in FPGAs. Now, normally a GA is using an optimization technique, which means it attempts to find one optimum. In this case, we're changing that slightly to search for multiple good test cases. So we do that. So starting on the left, we start with a population of test cases, and then going through the loop, we first evaluate how fit or the quality of each test case. We're using the neural network-based critic to say how close does the drone fly to that obstacle configuration. And then we're using a leaderboard of test cases that we currently think are good to assess how novel that test case is. We then go through a selection phase where we update the leaderboard with the best test cases we have in our population at that time. We then do a genetic algorithm, does a selection approach, and also applies genetic operators to hopefully improve the population, and the process then repeats. At the end of that process, we then take that leaderboard, and that becomes our effective and diverse set of test cases that are then passed the Low-Fi estimator to reevaluate. Next slide, please. Lovely. Okay. So there's two components to this fitness function that's very important to understand. The first is the use of the neural network critic, to assess distance. You might ask, why do we bother doing that? The simple answer is because it's fast. So if we look at the numbers here, if we use the Low-Fi estimator, it takes about 1.5 hours to do 1,000 evaluations. Neural network critic takes 65 seconds. The reason being it's a feed-forward neural network. We can run calculations very quickly. The other component is novelty. We calculate that based on how novel the test is relative to those in the leaderboard as a distance measurement in the feature space. Therefore, you can see this as a multi-objective optimization to distance and also novelty. Okay, next slide, please, Anas. Lovely, and that kind of brings us into an end. So just to summarize then, the second edition of the competition took place at the end of last year, I believe. The tools are assessed on how effective they are and how diverse the tests they produced. Anas' winning entry generated samples that are both valid and effective. And then we're looking at using this GA and a neural networks-based critic to further look at how we can produce diverse test cases and evaluate the efficiency using neural network critic. Thank you very much.
Thank you.